Okay, can I start?
Just one thing, I would like to thank Don Chuaili for the translation. You will be very welcome to help us again. We have 2 more online presentations. Please come here. Please, Adonis, the floor is yours.
Thank you. Okay, thank you. Yeah, perfect. So I guess everyone can hear me now. Okay. Well, my name is Adonis Leal. I'm assistant professor at New Mexico Tech, and I do lightning research at the Lapierre lab. Okay, so let's start. So I'm going to present today a study that we use electric field measurements to estimate how much charge we transfer to ground during continuing current phase. And the caveat of this work is because we calibrate our system using Hockey trigger lightning. Okay, so let's move for the beginning. What is continuing current? What is the continuing current phase of a lightning flash, and how can we identify those continuing current phases in a lightning flash? So the characteristics of continuing current, if you look to the electric field, is the slope in the electric field, like the slope increasing or decreasing depending on the polarity that we are transferred between cloud and ground. Or if you have a high-speed video or any video, if the channel lasts longer, that means we are transferring a charge to the ground in a long period of time. Okay, and why we should care about long continuing current? Okay, because they can cause like damage for the electric power systems. They can damage, for example, renewable energy like the wind turbines. They can initiate wildfires because when we transfer a lot of charge to ground, we produce overheat, and that overheat can cause more damage than like a regular lightning strike. Okay, so let's move for the calibration. So one way to measure the continuing current is by putting a current sensor at the bottom of the lightning channel and measure the total current that we transfer between the cloud and the ground. And we did that at the Lapierre lab last year using Hockey trigger lightning. Well, if you integrate the current you measure over time, you can have the charge, the total charge. So that's what we did. So using the electrostatic approach and the method of image, we can arrive at this formula here. Okay. So it's very well established in the literature. It's a simple way to estimate the electric field change. Okay, and we have like some variables in that equation here. And one of them is the total charge we transfer to ground, the electric field change, the height of the charge layer, and the distance between the lightning channel and your electric field sensor. So if we solve for K, which is our calibration factor, we must know what is the total charge transferred to ground, what is H, what is D. So let's start with the charge, the electric field we measure, okay? So the total charge we transfer to ground, we have already because we measure the current at the bottom of the lightning channel. And we have an electric field sensor about 27 kilometers away. That electric field sensor has 4 channels, 2 fast channels and 2 slow channels. The fast antenna is about 1 millisecond decay time constant, and the slow one is about 10 seconds. But the other like caveat in this work is because we apply the drooping. So that word is something that arrived in our field like in the beginning of the 60s, 70s. But nowadays people use like different terminology, but at the end is find a slow change using a fast electric field. So it's compensated the fast electric field to get the slow field. And we did that because like most of the time when the lightning is nearby, we saturate this low field because we have a lot of electric field change. So we did that. So when we do that, we can see here that the differences between the dedrooped and the original slow field is minimum. So we could reconstruct the signal of 10 seconds decay time constant using only 1 millisecond of decay time constant. Okay, let's move to the other parameters that we have in our equations that are H and D. So H is the length of our lightning channel, okay? And how we measure like that length, like the position of the charge layer to the ground. So we use the LMA, lightning mapping array, okay? So using the LMA, we have the distribution of the VHF sources that is related to that lightning flash. We found here like the average height using this histogram here, and here is the ground level. So we use like terrain maps to find what is the ground level for each specific flash. If we subtract the Q height from the ground level, we have H. And D, we have D because we know the location of the two sites. So having delta Q, delta E, H, and D, we are able to find a very good calibration factor. So we have an accurate electric field measurement. So now we are able to apply to natural flashes. So we apply that methodology to natural flashes. The distance, the age, we use LMA to find the age for all flashes. The distance, we use Earth Networks lightning location system data. And the electric fields are the electric fields of our stations. Okay, so moving to the results. What are the main results here? So we compare our results to other studies in Brazil, Austria, US, and South Africa. And well, what we found is that like the average charge transfer to ground in our study is relatively high if we compare to other studies, like 31 coulomb in average. But well, the other thing that's higher in our study is the CC duration. Okay, so probably our result is biased because we pick only lightning flashes with long CC duration. Okay, and indeed, if we do the scatter plot of the charge transfer to ground versus the CC pulse duration, we can see a trend line that as we increase the CC duration, we transfer more charge to the ground. So, okay, so something that I did not mention, but is important, that only for negative cloud to ground flashes, okay? So we did the same comparing like the other studies here, like in South Africa, Brazil, Austria, and we found like the same trend line here. We try to investigate other variables. For example, how the charge transfer to ground is related to the height of the charge center, and we did not find any correlation so far. So the charge we transfer to ground is probably not related to the position of the charge in the cloud. So another thing that we investigate is the peak current of the return stroke that produce the long continuous current. So we also found not very good correlation between the peak current that produce that transfer such amount of charge to the ground. So basically, if we have a high peak current or a small peak current, it doesn't matter much. What matters the most is the duration of the continuous current. Finally, future steps. We're gonna try to trigger more to improve our calibration, because so far we have like just one trigger to calibrate our electric field system. and we're gonna move to get data for positive cloud grout flashes. We know that they are like not common. It's hard to get data from positive, but we're gonna try. So get more data to improve the statistics. That's all. Thank you for your time. Open for questions. I made it.
Thank you, Dr. Leal, for this interesting presentation, keeping the time. So,
yes.
The paper is now open for questions. Yes.
Wow, 3 questions.
We want to do that. Do you want to come here?
Halfway. Sorry, but 2 quick questions. Just when you're comparing with the other papers, they wouldn't have had LMA to estimate the height in that. Do you think? I think that would have just been done by looking at the isotherm.
Isotherm, yes, yes.
How much do you think that would that possibly explain your high value? Or?
Yeah, I was thinking about that, and I have like no answer for that right now. I think using LMA it's a more accurate way to get the height instead of the isotherm. But yeah, so maybe we could check in the future. So, yeah, I don't have an answer for that. If that methodology is increasing the charge transfer to ground.
And then just your correlation with the peak current, I'm surprised by that because I would have thought you're going to generate your higher peak current negative flash levels, generally a shorter duration. And then the lower peak currents would have a, so I would have thought there would have been a correlation. But
yeah, that's surprising as well because in the other papers we have that correlation. Like when we have small peak current, they last longer, right? But I'm not comparing the CC duration with the peak current. I'm comparing the charge transfer to ground.
So, Adonis, for that nice presentation. Just, I have the one question would be the same. Why didn't you see those exclusion zones, basically? But this is just a charge, so we don't really know. Maybe for the duration, you would see those exclusion zones.
Probably. Yes.
And the second question was, did I get that right that you used the average height based on the LMA sources and not point by point with the distance considering, because you just consider one distance. And yes, exactly, this graph.
Oh no.
These graphs.
Here we go.
And what if, did you maybe check the leader development? Because the leader, when it approaches your E-field measurement system, or it propagates away from your measurement system, this might have an impact on the estimated charge based on this formula.
Yes, that's like a very simple formula, right? We did not take into account a lot of stuff. So probably a future step is to apply a more realistic way to measure.
Just correct for the distance, exactly.
Yeah.
Where it propagates and see what the difference is.
Yes. Thank you. Thank you for your comment.
Yeah, maybe one small question regarding when you have on the graph, a calibration graph, when you have a current graph and the E graph, maybe I missaw it, but there are second units, is that right, or milliseconds?
Oh, seconds.
Very high duration. Oh, sorry. Okay.
Seconds. Yeah, so the ICC phase lasts for about like 500, 600 milliseconds, half of a second about the ICC duration. So yeah, we calibrate based on the ICC phase of the rocket rig lightning.
Very nice work.
Thank you.
About the point charge assumption, because LMA showed that it's not a point source, and we know already embedded another natural line, the charge could be very spread in a large area, yes. And also the fact with the distance with your station can matter. So any comment on that? The approximation of a single point charge.
Oh, I see your point. Yeah.
We did similar analysis in Kennedy Space Center, analyzing, but we use field mills in that case. And when the storms were approaching, the point charge was okay, but once the storm was above us, the point charge failed.
It's everywhere, right? The point charge is everywhere.
The charge, the sensor, the station under the charge is not.
Yeah. So probably the next step, instead of using a point charge, maybe we're gonna try like a disk of charge on like in the layer. Like we're gonna try different geometry. Yeah, we understand like the point charge is like very trivial here, like a simple case.
Depends what you do the station with respect the charge.
Yeah, so for example, let me see the results here. Yeah, in the table, the distance, here we go. Like that, the minimum distance is like 5 kilometers and the far distance is like 54 kilometers. So that's the range of distance for all flashes. So we have nearby and we have far away flashes.
Maybe one last question from my side. The formula that you used, you said is a very simple one, apparently effective. What about propagation effects of the field along those 27 kilometers? I mean, if you move to another location, because lightning, you
Yes.
want to apply that for anywhere.
Yeah.
What about propagation effects?
Yeah, we did not take into account any propagation effect, and maybe is affecting somehow because like the trigger facility is like no top of a mountain, like 3,000 meters away of like sea level. However, like that approach for calibration, we are calibrating against the current. So we have the current at the bottom of the channel and we have the field some like 27 kilometers away. So at the end, we are taking into account the propagation effect in that direction, but not in other directions. So probably, yeah, we have to investigate that. Thank you.
Okay, thank you.